All right, let's do a couple of examples. Look at some of the consequences of this thing. I want to point out a couple of things. First of all, I think, and I fixed this in the notes, but I neglected to include the 1 over the size of, I neglected to include 1 over the size of the group in the cycle index polynomial when I was messing around with this last time. That's always true as well, so that when you go to actually apply the cycle index polynomial to count colorings, non-equivalent colorings for a group acting on a bunch of colorings, then all you have to do is just plug in all of the xi's equal to the number of colorings, and that's it. You don't have to worry about dividing by the group, its size of the group itself. After all, the subindex of the cycle index polynomial is G itself. G gives rise to all of these variables that we have in here, representing the size of cycles and the number of them multiplied together. And therefore, we might as well take into account 1 over the size of the group as well. So that's why I put this little 1/8 in here. So I have corrected that. Another thing I did is I put these things in here just to point out the fact that these coloring counts are simply gotten at by plugging 2, 2, 2, 2, and 3, 3, 3, 3 into the cycle index polynomial, okay? All right, so I also wrote out a formal theorem down here that kind of describes what it is that we're doing. So S is just any non-empty set of elements, and G a group of symmetries acting on that. That induces an equivalence relation on a set of M colorings of those objects. Then the number of non-equivalent M colorings of it under the action of G is just given by the cycle index polynomial, evaluated at all the variables equaling M, right, where M is the number of colorings. And again, really, this theorem is just a corollary of the Burnside theorem that we already have in our back pocket. It's just a matter of actually thinking about psi of pi, the number of colorings that are fixed by a permutation, and realizing that in the end, that's just a consequence of the orbit structure of those permutations. That was the important piece. So the first thing I want to do is I want to go back to an example we did last time and just kind of redo it. And that was this one right here with the 15 ball situation. Okay, so let's think about this. All right, so first of all, it was just rotations, right? So, so what was it again? I had 15 balls, 3, 4, 5, 1, 2, 3, 4. 1, 2, 3, and 1, 2, and then 1. Okay. And remember, we were kind of thinking about things the following way. We were saying, well, you know, we were kind of looking at this block of 4 balls and this block of 4 balls right here. And we were looking at this block of 4 balls right here. And we were kind of thinking about these 3 balls in the middle rotating, okay? So G itself was equal to what? Well, there was a few, but there was just 3 rotations, basically 120 degrees, 240 degrees, and 0 degrees. So we had 0 degree rotation, and again, rotation is in the clockwise direction, okay? Always. So, and then what else? We had 120 degree rotation and we had 240 degree rotation, okay? Now, to make this thing kind of work the way that we want to, and to really detect, you know, what the cycle structure of this thing would actually be, we actually are going to have to label all of the moving parts, and that in particular would mean the balls, right? So remember, there was like a little central rotation point, and this whole thing was rotating in this direction, right? So just to bear in mind, okay? So it looks to me like we're going to have a whole bunch of like 3 cycles or something. Okay, so for instance, so let's see here. Let's just go around and label everything. So I'm going to go and label all the balls. So it's going to be A, B, C, D, E, F, G, H, I, J, K, L. Okay, and then what about the middle? M, N, O. Okay. All right. So, so how in the world am I going to think about G in relationship to these things? Okay, so let's think about that. How are we going to think about G in relationship to all of these labelings that we've put on these balls? I think that we can do it. Okay, so what about 120-degree rotation? What's going to happen with that? Okay, so let's think about it. So first of all, 0-degree rotation, that's kind of simple. Okay, so G equals 0-degree rotation, A doesn't go anywhere. So there's just a single thing, a single cycle of length 1 for B, all the way to, what's the last one here? M and O, right? O is the last one. Okay, so that's the 0-degree thing written in cycle format. Okay, what about 120-degree rotation? Well, okay, so where does A go? A goes to C. A goes to C. C goes to I. Okay, and I goes back to A. Close it off. Okay, what's the next one? Well, let's see, where does B go? Okay, B, where does B go if I rotate this thing? Okay, so B is going to go to, let's see, D, E, F. B is going to go to F. Okay. If you think about rotating that thing around by 120 degrees, and then where's F going to go? F is going to go to J. And where does J go? J goes back to B. Okay, close it off. Dot, dot, dot. Okay. And there's just going to be a whole bunch of 3 cycles like that. And there's one in the middle that's just M, N, O. Okay, that's the simplest one. So how many total length 3 cycles are there in this particular thing? Well, there was 15 total balls. Each one gets their own label. Okay, so there's 5 cycles. There is 5 cycles of length 3. Okay, so that thing corresponds to 120-degree rotation. Finally, what do we have? What do we have for 240-degree rotation? We can kind of think about this. Now that we have the hang of it, it should be pretty easy. Okay, so 240-degree rotation, A goes to I. It's kind of like backwards rotation. A goes to I, okay? Where does I go? Well, I will go to E. Is that right? Let's see here. Is I going to go to, wait a minute, so I goes there, okay. Oh, I'm sorry. I think I meant that A back here went to E actually. I wrote C, but I meant E. A went to E, E went to I. Sorry, I was confused when I wrote that. B goes to F, and F goes to J. Yes. Okay. So sorry, I wrote C, but I meant E. Okay. So A goes to I. Okay. And then where does I go? Well, I goes to E. Okay. And where does E go? E goes back to A. Okay. And once again, what's going to happen when I have 240-degree rotation? Well, M is going to go to O. Okay. And where does O go? O goes to N. And N goes back to M. Close it off. Okay. So there's going to be a product of 5 things right here as well. Okay. And this thing corresponds to 240-degree rotation. Okay. 240-degree rotation. So what is the cycle index polynomial for this thing? So PG, okay, And how many variables am I going to have here? Think about it. I have a bunch of, I have some 1 cycles. Okay. I have some 1 cycles. And actually, the only other thing I have are a bunch of 3 cycles. Okay. So I go 1 over the size of the group, which is 1/3. Okay. And then I look over here. Okay. What about the first permutation right here? I have a bunch of 1 cycles, and there are 15 of those 1 cycles with the identity. So that's x1 to the 15th. Okay. And then I have a product of a bunch of 3 cycles. So I have 5 3 cycles, and that happens twice. So it's going to be 2x3, or oops, x3 to the 5th. x3 to the 5th, okay? And so if I want the number of 3 colorings, all I'm going to have to do is just plug in 3, 3. So the number of 3 colorings, which we got over here, is really just PG 3, 3. And indeed, we see that we're going to get the exact same formula. It's going to be 1/3, 3 to the 15th, plus 2 times 3 to the 5th, which is pretty interesting. One thing you might be noticing that's going on is that whenever you take each one of the summands, whenever you take the bottom number and the power, those two things have to multiply, and you like add them all together if there's several of them multiplied. All of those things have to add up to the size of the permutation itself. 1 times 15 is 15. 3 times 5 is 15. It has to account for every single cycle in the permutation itself. So it's going to be the size of the permutation. Okay, so hopefully that makes sense. Let's go down here and just kind of show that one more, or see that one more time. So here was our cycle index in the case of the square. Okay, notice right here, right? This is like to the first power basically. And notice that if I go 1 times 2 plus 2 times 1, I get 4, right? That means I had 2 1 cycles and 1 2 cycle, and that has to be the total number of elements in the permutation. And of course, this guy, I have 2 2 cycles, and that's also 4. And here I just have 1 4 cycle, so 1 times 4 is 4. Okay, and then this guy right here is just, 4 times 1 equals 4. Okay, so those things have to account for the length of the permutation every single time. That shouldn't be a huge surprise. Okay. All right, cool. Making progress. We have a nice way of expressing Burnside's theorem in such a way that really all we have to do is think structurally about a permutation and its cycle structure. The very beginning of chapter 9, I warned you starkly that cycle structure for permutations was going to be a very big deal for us. Okay? And we've kind of seen that play out in practice now for sure. All right. Let's do a couple of other examples here. Okay, so this is a problem from the book. I think I have you do maybe a couple of these in your homework set. We're just going to look at a couple of these for now. All right, so find the number of different M colorings of the vertices of the following floating figures. Okay, so the number of distinct M colorings of the vertices of the following floating figures. Now, if I'm going to float with these, that means I'm actually, I think I'm not just thinking about rotations. I'm also thinking about reflections themselves. Okay, so what do you think about this guy right here? Okay, let's think about this triangle. What's our G going to be? Well, the do nothing operation, 0 degree rotation, 120 degree rotation, 240 degree rotation. And then it looks like I'm going to have a few reflections as well. Like if I reflect in the vertical axis, that's one. Okay, if I reflect in this axis, that's another. And it looks like if I reflect in this axis, that's another one. Okay. Okay, so that is our group kind of described loosely. All right, so let's actually try to come up with a labeling for this, and subsequent to that, how this thing breaks down in terms of its cycle structure, so we can write down the cycle index polynomial. Okay, so let's call this guy A, this guy B, this guy C, this guy D, maybe. Okay. Well, what's going on here? 0 degree, well, that's just going to be A, B, C, D. It's a bunch of 1 cycles, okay? All right, so what about 120 degree rotation? Well, A goes to B, B goes to C, C goes to A. And D, of course, is off on its own. That's kind of interesting. Okay, what about 240 degree rotation? Well, A is going to go to C, okay, C is going to go to B, and B goes back to A, right? That's kind of like going backwards, okay? And of course, D is still off on its own, okay? Let's see here, what else do we have? Well, those are our rotations. What about reflections? Well, if I reflect in the vertical thing, A and D are both fixed. A and D are both fixed. And what's up with B and C? Well, they just flip back and forth. Okay, similarly, if I reflect in the positive slope axis, it looks to me like C and D are going to be fixed. Okay, and so C and D are going to be fixed, and A and B are going to flip back and forth. Okay, and if I reflect in the negative slope axis, what's going to happen? Well, B and D are going to stay put, and A and C are going to flip back and forth. Okay. Interesting. Okay, so what is the cycle index polynomial for this thing? PG. Okay, now I look at this and I say, all right, what kinds of cycles do I have? Well, I have 1 cycles, I have 2 cycles, and I have 3 cycles. That's how I determine the cycle index polynomial. So I have the variables for it. I have 1 cycles, I have 2 cycles, and I have some 3 cycles. Okay. 1 cycles, 2 cycles, and 3 cycles. All right, so first of all, I go 1 over the size of the group. Okay, so I have 1, 2, 3, 4, 5, 6 different permutations. Okay, so I have the identity element. That's going to be 4 1 cycles, so that contributes an x1 to the 4th plus. Okay, so what about other things? Well, I have a couple of 3 cycles and 1 cycle in there as well. So there's 2 of those. So it's going to be 2 x1 to the 1st power times x3 to the 1st power. Okay, that comes from the 120 and the 240 degree rotations, plus what? Well, let's see here. It looks like I have 3 cycle structures that are exactly the same. This is amazing. Like all these elements, all that matters is their cycle structure, and that uniquely determines the sum and they contribute to the cycle index polynomial. So that's remarkable. So let's see here. There's 3 of these, and it's going to be x1, okay, squared times what? X2 to the 1st power. Okay, and each time you can tell, right, because after all, these are raised to the 1st power, right? This is raised to the 1st power. 1 times 4 is 4. 1 times 1 plus 3 times 1 is 4. 1 times 2 plus 2 times 1 is 4, right? So all is right with the world there. Okay, and I want the number of M colorings of this thing. So the number of M colorings, number of distinct, I should say, let me see. I should say something like M, or I should say the number of G distinct, okay, number of G distinct, because really it depends on what the group is, what the action is on the shape at hand. Number of G distinct M colorings equals what? Well, it's going to be PG of MMM by the cycle index polynomial counting formula, okay? So we're going to get 1/6 m to the 4th plus 2m squared, let's see, plus 2m squared, okay, plus 3m cubed, which is very interesting indeed, plus 3m cubed, okay? So no matter what number of colorings we're working with, we immediately know what the formula is for the number of distinct colorings here. By the way, I could have also talked about colorings of edges, and the analysis would have been very similar. I would have just had to label edges. What would the difference have been in such a case? Well, instead of 4 things moving around, would have been 6 things, but I would have had the same permutations acting. This is why at some point I made a really big deal about the fact that really we have permutations induced by these symmetries on the vertices, okay? But, you know, we're just, now that we know how cycles are working, and we see that all that really matters is the cycle structure and how it's working on the objects that we're trying to color as we rotate and reflect things around. We have a really clear understanding, a much clearer understanding of what's happening. So I know that we're playing kind of fast and loose with these permutations, but hopefully you understand kind of what we're doing here for the most part. Okay. I think I'm actually going to stop right here because tomorrow the photographer, videographer at Cedarville is going to come and take some pictures of the sort of thing that I've been doing in my classes. He's been going around and doing that apparently. So I'm going to do a bunch of examples tomorrow in class. I'll also take questions as I normally do. So if you have questions, that will definitely be the priority. But I will also do examples, you know, related to these ones that happen to be sitting right here. But also I'm going to do some examples with more interesting figures. In particular, I'll look at the so-called Platonic solids. I'll look at the tetrahedron. I will also look at the tetrahedron. I'll also look at things like the icosahedron and the dodecahedron, maybe even the octahedron. Okay, and we'll kind of think through, and even the cube. Why not? Let's just we'll look at the cube also, and we'll talk about different kind of coloring things like potentially the faces of these Platonic solids, or the vertices, or the edges. And we'll look at how things change when we do that, but really how things also stay the same. We have fully prepared ourselves to do a lot of really technical coloring problems with a fair amount of ease by making use of the cycle index polynomial. And the reason we want this really generic structure with the xi's in here is we're about to use it to get something amazing, namely Polya's enumeration formula. And that involves not just counting colorings, but actually categorizing them by the number of each type of color that happen to appear. Okay, so that's going to be the ultimate goal of all of this stuff. But that is to come. Bye for now.